Hello, we are now on the final period, and on the final period, so we will be covering higher order differential equations as our start. So there are three methods in solving higher order differential equations. So the first one would be through the homogeneous equation, or homogeneous with constant coefficient. The second method is non-homogeneous with undetermined coefficient. And lastly, we have the variation of parameters. So those are the three methods in finding the solution of a higher order differential equations. Depending on the type of higher order differential equations, so will tell us what method are we going to use in finding the solution of it. And then afterwards, so once we are done with those three methods, so we will be covering the variation, or we will be covering the Laplace transformation. So Laplace transformation is another method, or it is an alternative method. So in finding the general solution of a differential equation. So it's because not all of the methods available, so for higher order differential equations, so can be resolved using those three methods that was mentioned. The Laplace transformation so could solve, okay, so potentially more types of differential equation, so as compared to the homogeneous and non-homogeneous methods. And that will be the coverage of the finals, so the methods for higher order differential equations and the Laplace transformation. So for today, so we will be introducing higher order differential equations. So from the previous meetings, so both for prelims and midterms, so we covered the first order differential equation and its application. So this time around, so we will be covering higher order differential equations. So when we say higher order differential equations, remember the order of the differential equation so would correspond to the highest derivative. Okay, so the highest derivative on the differential equation. So in the first order differential equation, so if you have noticed, so we are only dealing with first derivative type of differential equations. So for higher order differential equation, so that would start with a second derivative, or a differential equation that contains a second derivative and even higher. And if you could still recall on our introduction, so we have mentioned before that the number of solutions in a differential equation corresponds to the order of the differential equation. So a first order differential equation has only one solution. And then a second order differential equation so would have two solutions. A third order would have a three solution. A fourth order will have a four solution, and so on and so forth. Okay? So the order of the differential equation so will correspond to the number of solutions of the given differential equation. So for higher order differential equation, so there are two types of it. Okay? So the homogeneous equation and the non-homogeneous equation. So this homogeneous equation is different with the homogeneous that we have talked about in as a solution, okay? As a substitution method for first order differential equation. So homogeneous equation, so this is a higher or homogeneous equation, so our equations, okay? So our equations, so in which a differential equation involves only the dependent variable and its derivative. Okay? The dependent variable together with its constant coefficient and its derivative on the equation. Okay? So if it only involves the dependent variable, so let's say it only involves y and its derivative, so y prime, y double prime, y triple prime, and so on. So therefore, that equation is considered to be homogeneous. But when we say non-homogeneous, So that is a differential equation which contains the dependent variable y, its derivatives, and other functions as well. In that case, that is what we are referring as the g of x. So as you can see on here, so the homogeneous equation, so this would be the format. So this would be an equation that involves, okay, the dependent variable y and its derivatives only. Then this is equated to 0. So that is a homogeneous equation. But if the differential equation contains, again, the dependent variable y and its derivative, and at the same time, it contains g of x. Okay? So that would be an additional function. Okay? So that's an additional function. So other than the dependent variable and its derivative, then that is considered to be non-homogeneous. Okay? So this one is a non-homogeneous equation. So example of which, let's say y triple prime minus 2y prime plus 4y is equals to 0. So in here, so we have the dependent variable y and its derivatives, the first derivative and its third derivative. And there are no other functions involved. So therefore, that is considered as homogeneous equation. But let's say we have y triple prime minus 2y prime plus 4y is equals to sine x. So this would be the dependent variable and its derivative. And then it contains another function. So that would be a sine x. Then that is considered to be, okay, so that is considered to be a non-homogeneous equation. So if the g of x is a trigo, okay, so in this case it's a trigo function, an exponential function, a logarithmic, a hyperbolic, or possible, it could be algebraic as well, that would be considered as a non-homogeneous equation. There are some instances, for example, if I would have y triple prime minus 2y prime plus 4y is plus 1 is equals to 0. As you can see here, so sometimes we are tricked with this one. So there is a derivative, or there is a dependent dependent variable y, as well as its derivative y prime and y triple prime. However, we have a constant here. So constant there, so that would already be considered as another function. Okay, so it's another function. So therefore, this one is considered as a non-homogeneous as well. Okay, so remember, in homogeneous equation, it only involves the dependent variable y and its derivatives. So if it contains dependent and its derivatives together with other function, so whether that would be an algebraic function, a trigo function, an exponential, a logarithmic, or a hyperbolic function, then that is considered as a non-homogeneous equation. So why do we need to determine whether the equation is homogeneous or non-homogeneous? So as I've mentioned, there are three methods. Okay, so there are three methods in solving or in finding the solution of a higher order differential equation. So when we say it's a homogeneous equation, so the method that we will be using would be the methods for homogeneous with constant coefficient. So that's the first method, okay, so that we will be talking. So homogeneous with constant coefficient, so this method is used for homogeneous equations. While if we have non-homo, okay, so non-homogeneous with undetermined coefficient. So this is used for non-homogeneous equation. And the last method, so which is the variation of parameters, is used as well. Okay, so it is used as well for non-homogeneous differential equation. So in short, there is one method in solving homogeneous equations, and there are two methods in solving non-homogeneous equation. So non-homogeneous equation is limited with some parts of g of x. Okay, so however, for variation of parameters, as long as you can integrate it, okay, you can able or you'll be able to use the variation of parameters. However, for non-homogeneous equations, so once we or with undetermined coefficient, so once we go to that topic, it's limited only to specific values of g of x that it can solve. So if it can no longer be resolved using non-homogeneous with undetermined coefficient, so we can use the variation of parameters. And variation of parameters is limited as well. So if it's already too complex to integrate it, we can already employ the Laplace transformation in finding the solution. Okay, so that is how we solve, okay, or how we find the solution of a higher order differential equation. Okay, so let's proceed with the first principle that we need to consider. So in solving or in finding the solution of a higher order differential equation, and that is what we are referring as the superposition principle. So let y1, y2, and y sub k, so those are the solutions of the differential equation depending on the order of the differential equation. So the order of the differential equation would correspond to the solution of the differential equations. So given those y1, y2, and y sub k, so these are the solutions of the homogeneous nth order differential equations on the interval I, then the linear combination y is equals to c1 y sub 1x plus c2 y sub 2x until c sub k y sub k of x, wherein the arbitrary constant c, wherein I would be equal to 1, 2 until k, our arbitrary constant, is also a solution on the given interval. Okay, so that is what we are talking about, the superposition theorem. So later on, so we will be using, the superposition principle, so in expressing our general solution on a differential equation. So remember, in a differential equation, so we don't have a single solution only. Okay, in a higher order differential equation, so we have multiple solutions. But how do we express? Express the general solution of the differential equation if there are multiple, solutions of it? So we are not just going to write it as one by one, but rather, so we can compile them into a one general solution. Okay, so into a one general solution that would fit, that would serve as the solution of the higher order differential equation. And that one can be done using superposition principle. So we will clarify those things so as we proceed with our discussion. So for example, so we have a second order differential equation. Okay, so a second order differential equation, so let's say it has this format. So a y double prime plus by prime plus cy is equals to 0. So that is our second order differential equations. And then once we were able to prove that a y double prime plus by prime plus cy is equals to 0, then therefore that is considered to be a solution of the differential equation. So for example, I have the second order differential equation, and one of the solution, okay, so let's say y is equals to h of x is a solution of the second order differential equation. So y is equals to h of x is a solution of second order differential equation. So let's prove that this is really a solution of the differential equation. So to do that, just like in the verification of the solution of a differential equation, so we just need to find, the derivatives, and then afterwards we're just going to substitute. For example, so y prime, so the first derivative of y, so would be equal to h prime of x. Similarly, so y double prime, or consequently y double prime would be equal to h double prime of x. Then we're just going to substitute. So a y double prime is equals to h double prime of x. And then plus b y prime is equals to it's equal to h prime of x. And plus c, then y is equals to h of x is equals to 0. As you can see here, h double prime of x, h prime of x, and h is the same as y double prime, y prime, and y. So we're just using different variables. So instead of y, we're using h of x, and this one, it's still be considered to be equal to 0. So based from this, okay, so that a y double prime plus b y prime plus c y is equals to 0. So in this case, therefore, a h double prime plus b h prime plus c h of x is equal to 0 as well. Okay, so we're just using different variable. So therefore, 0 is equal to 0. And thus, okay, so and thus, y is equals to h of x is considered to be, okay, so it's considered to be a solution of the given differential equation. Okay, so that's how we prove that this solution is really a solution of a differential equation. So another thing is, what if there is a solution? Okay, so let's say one of the solution is e raised to x. Okay, so one of the solution is e raised to x. What if I'm going to attach a constant, let's say a 5, e raised to 2x. So if y e raised to 2x is a solution, will the attachment of a numerical coefficient, okay, so to the given solution, become another solution of the differential equation? So let's try to verify. So as I've mentioned, so if I would have, this is what we've done. So initially, we have a solution which is y is equals to h of x. But this time, so we attach an arbitrary constant k, and we're just going to verify whether this is still a solution of the differential equation. So just like what we did, so we're just going to derive. So k y prime, so would be equal to k, then h prime of x, and then y double prime would be k h double prime of x. Then we're just going to substitute on the same equation, just like this one. So we have this equation. So a, then, so y double prime is k h double prime of x. Then b, y prime is k h prime of x. Then plus c, k h of x equals to 0. As you can see here, k is factorable. So k then would be equal to a h double prime of x plus b h of x, then plus c h of x is equals to 0. However, remember that this is 0. So therefore, that is k is equals to 0, or k times 0 is equals to 0, and 0 is equals to 0 as well. Okay, so from this proof, okay, this only prove, okay, that if we have e raised to 2x as a solution, so if I am going to attach an arbitrary constant, okay, an arbitrary constant to the solution, okay, so by multiplying our arbitrary constant to the solution, then that is still a solution of the differential equation. So if this is a solution, okay, so if this is a solution, so attaching a constant or multiplying a constant to the solution, so this one still makes a solution of the differential equation. Okay, so that's the second idea that we have. Okay, So one is verifying the solution. The other one is if we're going to multiply a constant or a coefficient, constant coefficient to the solution, will it still be a solution? Yes, it is still a solution of the differential equation as proven on our process. What if we have two, it's a second order differential equations, and then there are two solutions. There are two solutions that are present. So one is h of x, the other is g of x. So it's the second order differential equation. So therefore, there are two solutions that are present. In this case, we have the y sub 1, the first solution, and then the y sub 2 as the second solution. So if I am going to add, those two solutions, so forming a general solution, okay, will it still be a solution of the differential equation? So let's find out. So let's try to derive. So y prime, so would be equal to h of x plus g prime of x. Then y double prime is equals to h double prime of x plus g double prime of x. So in here, so substitute it with our equation. So we have a, multiply it with y double prime as h double prime of x plus g double prime of x. Then plus b, y prime is h prime of x plus g prime of x. Then plus c, h of x plus g of x is equals to 0. So let's try to regroup. So distributing all the coefficient a, b, and c. So this will form as the a, h double prime of x plus b, h prime of x, then plus c, h of x. And again, so plus b, a, g double prime of x plus b, g prime of x plus c, g of x equals to 0. And as you can see here, this is 0. Again, this is 0 as well. So therefore, 0 is equals to 0. So in short, if we're just going to add, okay, so we're just going to add two solutions, okay? In this case, the two solutions of a differential equation. We're just going to add those two solutions. So forming the general solution of the differential equation. So forming the general solution of the differential equation. Will it be a solution, still a solution of the differential equation? Yes, it is still a solution of the differential equation. And that is what we have proven on our process here. And actually, this thing that I am talking is what I am referring as the superposition principle. Okay? So the superposition principle is actually this one. So wherein if there are two or more solutions of a differential equation, taking the sum. Okay, so taking the sum of all those solutions, so forming the general solution of the differential equation, it is still a solution of a differential equation. Okay, so that is how we express. Okay, so that is how we express the general solution of a differential equation. So we just only take the sum, okay, of all the solutions, so forming the general solution of the differential equation. Okay, so that is, those are the principles, okay, so in expressing the solution of a differential equation. So next, so our next topic is, this is about the characteristic of the solutions of a differential equation. Given all the solutions of a differential equation, the specific solutions. So let's say if it's a second order there are two solutions that are given, the y sub 1 and the y sub 2. Without even substituting it to the original differential equation, because the way on how to check so whether those are a solution or not, okay, the way to check whether those are a solution or not is we're just going to find the derivatives of those solutions, and then we're just going to substitute it with the original equation, and from there, so we'll be able to determine so whether those are solutions or not. But that is a very tedious process. It's a very long process, especially if the solution is long. There's an alternative, okay, so on how to determine so whether those two or more solutions are really a solution of a differential equation by determining the linear dependency of the solutions. Okay, so it says here that a set of function f of 1x, f of 2x, f of n of x is said to be linearly dependent on an interval if there exists constant c1, c2, c sub n, not all 0. So such that c1 f of 1 of x plus c2 f2 of x plus cn f of n of x is equal to 0. So if we were able to satisfy that one, that is a linearly dependent. Those solutions are linearly dependent with each other. But if we could not satisfy that one, that is considered to be linearly independent. But what's the significance of these? So actually, solutions of differential equation of higher order differential equation So solutions of higher order differential equations are actually linearly independent. So that is one of the characteristics. Okay? That is one of the characteristics of the solutions of a higher order differential equations. They are linearly independent. So that's the significance of knowing. So whether the differential equation is linearly dependent or linearly dependent. So linearly independent, those are solutions of a higher order differential equation. So that's a characteristic of the solution of a higher order differential equations. Linearly dependent, those are not. Okay, so those are not. So but how do we classify? So whether the solutions are linearly dependent or linearly independent. So there are two methods. So the first method is finding a value. Okay, so finding a value for all the arbitrary constant, and then we're just going to guess. Okay, so we're just going to guess the values of C1, in this case C2, and the C sub n. So if we're going to substitute that one, and then it equates to 0, that is linearly dependent. Given that C1, C sub 2, until C sub n, not all of them will be equal to 0. Okay? So, hindi pwedeng lahat. Kasi, if we want to make that equal to 0, okay, we're going to make C1, C2, C sub n equal to 0. So, therefore, it will become 0. Okay? That is an exemption to the rule. Possible that 2 are 0, but another one is an integer, that would be okay. Okay? Pero what is not allowed is all of the arbitrary constants are all zeros. Okay? Pero if there is a combination of the arbitrary constant, okay, in such a way that if I'm going to multiply it on the given function, and then it became 0, okay, it became 0 eventually, then that makes it linearly dependent. But if we could not think of any combination or any value of all the arbitrary constants that will make it 0, then that is linearly independent. Okay, so to understand what I am talking, so for example, I have a third order differential equations. Then the first solution is x. The second solution is x squared. The third solution is 4x minus 3x squared. Okay. I could not verify whether these are really a solution of a differential equations. Okay. These are a solution of a third order differential equation because I need to check whether this is linearly dependent or linearly dependent. So we'll verify. So to verify that, so we just need to think of the values of C sub 1 and C sub 2 and C sub 3 that would make it equal to 0. Okay, so that will make the equation equal to 0. But take note that C1, C2, and C sub 3 should not all be equal to 0. Okay, so take note of this. So C1 should not all, C1, C sub 2, and C sub 3 should not all be equal to 0. Should not all be equal to 0. On how to do that, so since this is algebraic, it would be AC, right? So if I'm going to multiply C3 times 4x, so that would be 4C3x. So given that 4 will not absorb, will not be absorbed by the arbitrary constant C sub 3. So in this case, I'll have 4, okay, so for C sub 3, so therefore for C sub 1, so I could think that that should be a negative 4 for C sub 1. And then for C sub 2, so C sub 2 is x squared. However, C sub 3 is multiplied with a negative 3 x squared. Okay? So I could think that C sub 2 would be 3. And then C sub 2 is 3, C sub 3 would be 1. So substituting this to the equation, so that would make it, by the way, we're using the superposition theorem in forming the general solution of the differential equation. So C sub 1 is negative 4, so negative 4x, plus C sub 2 is 3, so plus 3x squared. Then plus C sub 3 is 1, so 4x minus 3x squared, so equals to 0. So you can see negative 4x plus 4x is 0. 3x squared minus 3x squared is 0. So therefore, 0 is equals to 0. So since this is 0 is equals to 0, that would make it linearly dependent. Okay, so let's have our second example. So we have 3 solutions. So one is 5, the other is cosine squared x, and the other is sine squared x. So we're assuming that these are a solution of a third order differential equation. So if those are linearly independent with each other. But let's try to verify. So using superposition principle, so multiplying 5, so with an arbitrary constant C1, and then taking the sum of all the solutions, so plus C2 cosine squared x plus C3 sine squared x equals to 0. So as you can see here, so we have 5 for C multiplied with C sub 1, and then cosine squared x and sine squared x, so once we combine them, so that will form a Pythagorean identity, so which is equivalent to 1, right? So if I'm going to have C1 to be equal to negative 1, and then C2 to be equal to 5, and C3 to be equal to 5, so that will yield to 5, C1 is negative 1, so plus 5 cosine squared x, plus 5 sine squared x is equals to 0. So this would be negative 5, and plus, we could factor out 5, that would make it cosine squared x plus sine squared x is equals to 0. So remember that this is a Pythagorean identity which is equivalent to 1. So making it negative 5 plus 5 is equals to 0, and 0 is equals to 0. So therefore, that would make it linearly independent. Or sorry, linearly dependent, since it is equal to 0. So linearly dependent, and therefore not a solution. of a differential equation. Okay, so not a solution of a differential equation. So since that is equal to 0. So there's no value, or there are values of c sub 1, c sub 2, c sub 3 wherein not all of them are 0. So that would make it equal to 0. Those are not a solution. So how about for the third one? So we have 1 plus x is equals to, then the next one is x, the other one is x squared. I have 1 plus x, and then x, and then the other one is x squared. So as you can see here, x squared is multiplied with c3. Okay? And there's no x squared on c1 and c2. So therefore, if I want to make that equal to 0, so I need to write 0 for c sub 3. Okay, so c sub 3 multiplied with x squared, so 0, so that would make it 0. However, for c sub 2, so we have x, okay, so this is x, the other one is positive x as well. So probably I could make c1 to be equal to negative 1, or c2 to be equal to negative 1. So negative 1 then, so c2 would be negative x, given that c1 should be equal to 1. So c1 is equals to 1, and then that would make it x minus x, so that would make that 0. However, if c1 is equal to 1, so therefore, this is 1 as well. Okay, so c1 times 1, or 1 times 1, still 1, and 1 is not equal to 0. Okay. The only thing, okay, so that would make it 0 is if we're going to make c2 is equals to 0 as well. Okay. But if we make c2, okay, to be equal to 0, okay, so the only way to cancel out 1 plus x, so would make c1 to be equal to 0 as well, which is not allowed. Okay? The c1, c2, c sub 3 should not all be equal to 0 to make the entire equation equal to 0. So since this is an exemption to the rule, so therefore, there is no value. Okay? So there is no value for c1, c2, and c3. So that will make the sum, okay, of the given differential equation to be equal to 0. And thus, those solutions are linearly independent. And therefore, those are a solution of the differential equation. Ibig sabihin, itong tatlong na to, those are a solution of a given differential equation. Yung unang dalawa, they are not. Okay? So those are the methods. Those are the methods in finding whether the solutions are linearly dependent or linearly independent. So if it is equal to 0, there are values for c sub 1 or for the arbitrary constants that would make the equation equal to 0, then that is linearly dependent. And it is not a solution of a differential equation, just like the first two examples. While if there are no values of c sub 1, c sub 2, and c sub 3, so that would make equal to 0 other than all of them, or other than all of the arbitrary constant to be equal to 0, then that those are linearly independent solution. And thus, that is a solution of a differential equation. Okay, so that is the first method in determining the linear dependency of a given equation. Okay, so that is on how to find whether that is linearly dependent or not. So there is another method on how to check So whether it is linearly dependent or not. That is what we are referring as the Wronskian method. So in the Wronskian method, so we will be using matrices. Okay, so depending on the number of solutions. So if it is a second order, so we will be using a 2 by 2. So when I say a 2 by 2 matrix, so it has two rows and 2 columns. If it is a third order differential equation, so there are 3. Okay, so there are 3 solutions. And that would be a 3 by 3. So in solving the matrix, so parang kamukha nung kanina. If it is equal to 0, it is linearly dependent. If it is not equal to 0, it's linearly independent. It's equal to 0, it's linearly dependent. If it's not equal to 0, that would be linearly independent. But how do we form the matrix? As you can see here, so the first row, so will correspond to the solutions. Since this is second order, so f of 1 of x is the first solution, f2 of x is the second solution. If it is a third order, f1 of x, f2 of x, and f3 of x would be the solution of a third order differential equation, the 3 solutions. Then if there are 2 solutions, so we need 2 rows. There are 3 solutions, we need 3 rows. So we need a square matrix. So kung dalawa, dapat 2 by 2. Kung tatlo, 3 by 3. Yung apat, 4 by 4. Okay. But the given is only the first row. So how do we get the second row? How do we get the third row? So by just deriving the equation or by just deriving the solution. So in this case, so the second row will comprise the first derivative of the first solution and the first derivative of the second solution. So if it is 3 by 3, so the second row would be the first derivative, the third row will be the second derivative. And then we're just going to find the determinant. Okay, I'm not sure whether you're familiar with that method or not. Later on, we'll try to show how to find the determinant of a 2 by 2 and a 3 by 3 matrix. But take note that if the Wronskian value is equals to 0, that makes it linearly dependent. If the Wronskian value is not equal to 0, that makes it linearly independent. So this is a solution, again. So this is a not a solution. Not a solution. The other one is a solution. So let's have a simple one. So f1 of x is x squared, f2 of x is 2x. So the Wronskian value here, so the matrix will then be our f1 of x is x squared, the second is 2x. So to form the second row, so we're just going to derive x squared, derivative is 2x, derivative of 2x is 2. So that makes it a 2 by 2 matrix. So for a 2 by 2 matrix, to find the determinant, okay, so to find the determinant, we are just going to get the product of the downward element minus the product of the upward element. So this is only true for a 2 by 2 matrix. The product of the downward element minus the product of the upward element. So therefore, W here will then be equal to x squared times 2. So that would be 2x squared. Okay, so 2x squared. Then minus upward, 2x times 2x, that would be 4x squared. So W is equal to negative 2x squared. And as you can see here, so W is not equal to 0. So therefore, it is linearly independent and thus a solution. A solution of differential equation. Sandali, di ba? So you're not going to think of the values of C sub of the arbitrary constant. So we're just going to find the determinant. So for a 2 by 2 or 2 by 2 matrix, so this is how we will be doing it. Okay, so downward minus upward. So let's have another example. So for our other example, so we can see here that this is the same as the third one. So 1 plus x, and x squared, right? Sorry, it's not. Okay, so the first one. So it's the same with the first one. So our answer here is linearly dependent and it's not a solution. So using Wronskian method, so we should yield on the same answer. It should be linearly dependent, it should be equal to 0 and not a solution. But since this is a 3 by 3 matrix, or since this is a 3 solution, so our matrix would be a 3 by 3. So W then, so would be equal to x, then we have x squared, then we have 4x minus 3x squared. So this would be 1, this is 0. First derivative is 2x, this is 2. So this would be 4 minus 6x, and we have minus 6. So 4 minus 3x squared, 4 minus 6x, and minus 6. Finding the determinant of a 3 by 3 matrix is different with a 2 by 2. In a 2 by 2, it's just simple, the downward minus the upward. But for a 3 by 3 matrix, so this is how we do it. Okay, so we're going to augment the first two columns. Okay, we're going to augment the first two columns. That is, the first column is x, 1, and 0. The second column is x squared, 2x, and 2. And then afterwards, so we're going to get the sum of the product of the downward. So that means, so this one. Take the product of the diagonal, then add the second diagonal, and then add the product of the third diagonal. And then once you take the sum of it, so subtract the sum naman of the upward. So this is the upward product of that, product of the second diagonal, and product of the third diagonal. So that would make it then to be equal to, so W, so the first diagonal, so that is x times 2x times negative 6. That would be negative 12x squared. And the second one is we have x squared times 4 minus 6x times 0. Okay, so the good thing here, it's multiplied with 0. So therefore, the whole thing would be 0. That is plus 0. And then take the product of the last term. So that would be 1 times 2 is 2. So distribute it with 4x. That would be plus 8x. And then minus 2 times 3. So we'll have 6x squared. So that would be the downward, the red. And minus the upward. So this is 0, 2x, and 4x minus 3x squared. So that would be 0. And then 2 times x is 2x times 4. That would be plus 8x. Then minus 2 times 6 is negative 12x squared, negative 12x squared. And lastly, so negative 6 times x squared will have negative 6x squared. So as you can see here, so negative 12x squared minus negative, so that would make it plus, so that would be 0. 8x minus 8x, 0. Negative 6x squared, negative negative plus 6x squared, that would be 0. So W then would be equal to 0. So therefore, that is linearly independent. And a solution of a differential equation. Or sorry, it should be not a solution and not, it's linearly dependent. So it's equal to 0. Linearly dependent and not a solution of a differential equation. So checking again, yung first example natin is 1. Okay, so when we just assume the values of C1, C2, and C3, so the answer is linearly dependent. So because it is equal to 0, and in Wronskian, it is equal to 0 as well. It is also equal to 0 as well. We have an alternative method actually. Okay, so we have an alternative method. I said this one is very long, especially if the derivative is very long. Okay, so that's the disadvantage of the Wronskian method. If the derivative would be long, so therefore our solution would be longer as well. So that is why an alternative method is that we need to derive first. Say this is the same. Alternative method. So x squared for x minus 3x squared. So x squared for x minus 3x squared. First derivative, second derivative. Okay. First derivative and then second derivative. And then from here, so that it will be easier, okay, so what we will be doing is we're going to substitute, okay? Kasi para mahirap i-multiply yung mga variables, no? We're going to substitute any value. Okay, so pinakamadali would be 1. So W then, so would be equal to x is 1. X is 1. And then x squared, so it's still 1. So 4x minus 3x squared is just 4x minus 3. Or that is just 4 minus 3, which is 1 as well. And then we have the constant. Okay, so for the constant, so we're just going to write the constant. Then 2x, 2 is 1, or x is 1, so 1 times 2 is 2. Then 4 minus 6 is negative 2. And then we'll have 0, 2, and negative 6. Yeah, so 1, 1, 1, 1, 2, negative 2, 0, 2, negative 6. And then just like what we did, so we're just going to copy the first two columns, augment it, and then we're just going to do the same process. Kaya lang dito, puro constant na sila. So madali nang i-multiply. Tapos upward, so W then would be, so 1 times 2 times negative 6 is negative 12. 1, negative 2, and 0 is 0. 1, 1, and 2 is 2. Then minus 0, 2, 1, that is 0. 2, negative 2 times 1, it's negative 4. The negative 6, 1 and 1, it's negative 6. So W then would be negative 12 plus 2 is negative 10. Then minus negative 10. So negative 10 plus 10 is 0. So therefore, linearly dependent and a solution. And not a solution. Sorry. And not a solution. Okay, so diba? So mas madali if we're going to substitute it with a numerical value. So let's have another one. So the 5 cosine squared x and then sine squared x. Okay, so solve this one as well. And our answer is, again, it's linearly dependent and not a solution. So it is equal to 0. So therefore, our answer here should be equal to 0 as well. Okay. Nakasulat na pala. So the first column is 5 cosine squared, or first row, 5 cosine squared x sine squared x. Then I'll have derivative of 5, 0. Derivative of cosine squared, it's negative 2 cosine x sine x. Sine squared is 2 sine x cosine x. And then using product formula, okay, so derivative ng cosine x sine x is equals to, so cosine x, derivative ng sine x is cosine x as well. Then plus sine x, derivative ng cosine is negative sine x. So that would make it cosine squared x minus sine squared x. Okay, so kaya lang meron siya negative 2. So that would make it negative 2 cosine squared x minus sine squared x. And then cosine squared x minus sine squared x. So siguro ang pinakamadali dito, so we're just going to let when x is equals to 0. So when x is equals to 0, that would be 5. So remember, if we have cosine 0 and sine 0. So cosine 0 is 1, sine 0 is 0. So cosine of 0 is 1, so 1 squared is 1. And then sine squared x. So sine 0 is 0, so therefore that would make it 0 here. And this is 0, this is 0. Sine 0 is already 0. Okay? So therefore, 0 na to. Ito, basta may sine, 0 na rin yan. And ito naman, so this is 1, this is 0. So that would be negative 2. Ito naman, this is 1, this is 0, that would be positive 2. And I have 5, 0, 0, 1, 0, negative 2. And downward, upward. So W then would be, so 5, 0, 2, 0. 1, 0, 0, 0. 0, 0, negative 2, 0. Minus 0, 0, 0, 0. Negative 2, 0, 5, 0. 2, 0, 1, 0. So therefore it is 0, linearly dependent, and not a solution. So again, in summary, the solutions of higher order differential equations are linearly independent. So that is when the Wronskian is not equal to 0, that is linearly independent. So that is on how to classify whether the solutions are linearly dependent or not.